Hello everyone. In this video we're going to be solving a nice problem with polynomials. So we're given that p of x plus p of x plus 1 is equal to 2x squared plus 2x plus 1. And we are supposed to solve for p of x, which means we're going to find an expression in terms of x for p of x. And what is p of x? You might be asking, right? Is that a function? But I use the special notation, and I'm telling you right now that p of x is a polynomial. What happens if p of x is not a polynomial, but it's just a function? Then you can't really solve for it, unless you make some assumptions. Can we still find a solution? That's a good question. And if this question was asking for something else, let's say something like, okay, what is p of 1 minus p of negative 1? At first glance, it doesn't look possible, right? Because if you replace x with 1, you get p of 2. If you replace x with 2, you get p of 3. You always get extra terms. So how on earth you're going to be able to get p of 1 minus p of negative 1? And again, I'm looking at it from a functional perspective, not necessarily a polynomial perspective, okay? And to find p of 1 minus p of negative 1, we would do the following. Again, it just comes down to substitution. First, we would substitute x equals 0, and you'll see in a little bit why that's helpful. This would give you p of 0 plus p of 1. Notice that we have to replace x with 0 everywhere. And then on the right-hand side, it would just be 1. And then the next step is crucial. Since we are supposed to find p of 1 minus p of negative 1, next we would replace x with negative 1. So what you replace x with makes a huge difference. That's why you need to be very careful about it, very cognizant about it. If you replace x with negative 1, you're going to get p of negative 1, which is replacing x with negative 1 basically. And then here you get p of negative 1 plus 1, which is 0. Uh-oh, that's a good thing to have, right? And on the right-hand side, if you replace x with negative 1, this is going to give you a 2. And then a minus 2, they're going to cancel out. And guess what? You're going to end up with 1 again. And here's the critical part. Since you're looking for p of 1 minus p of negative 1, all you have to do is first clear this area and then go ahead and multiply the second equation by negative 1, and that should give you negative p of negative 1 minus p of 0 equals negative 1, and just copy the first equation, which is p of 0 plus p of 1 equals 1, and then go ahead and add these equations up. What's going to happen? P of 0 is going to cancel out, and you're going to end up with p of 1 minus p of negative 1 equals 0. Uh-oh, what is that supposed to mean? It just means that p of 1 equals p of negative 1, which we don't really care about, okay? And you could probably see why that's happening. But anyways, that's a different story. This is not the real story. We are supposed to solve for p of x when p of x is a polynomial. How do you do that? So when you are given an equation like this, and if they tell you p of x is a polynomial, it's a good thing. You know why? Because you're only going to worry about a function of a certain form. So polynomials are special functions where powers of x has to be or have to be non-negative integers, which means you can have x to the power 0, which gives you the constant term. You can have x to the power 1, x to the power 2, x to the power 3, but you cannot have anything like x to the power square root of 3. You can't have x to the power negative 1. You can't have square root of x because that would mean x to the power 1/2. None of these are polynomials. Even though they have one term, they could still count as polynomials if they satisfy the criteria. So one thing that is super important about polynomials, first of all, you're kind of stuck because you have a single equation, but there seems to be two variables, p of x and p of x plus 1. So you kind of have to think about it very carefully. What kind of polynomial are we looking at? And when you need to talk about the kind of polynomial, how do you classify polynomials, right? We know that they have certain powers, and x, the domain, could be real numbers, but you could classify polynomials by degree. What does degree mean? So when you write a polynomial in the general case, like a sub n, x to the n, a sub n minus 1, x to the power n minus 1, so on and so forth. And as you know, the last few terms, like you get a1x plus a sub 0, which is a constant term, right? This is an nth degree polynomial. In other words, the degree of p of x, which I'm going to use this type of notation. I know that's not pretty standard, but let me just use this type of notation. In this case would be n. And n is a non-negative integer. So n can be 0, yes. If you have a polynomial that's a constant, it's of degree 0, but that's not very interesting, is it? Of course, if the degree is n equals 1, if the degree is 1, then you have something like this. P of x equals a1x plus a0, which means this is a linear polynomial. I know that's not how you write the I with a dot, but I just did. So it's linear because of the highest power of x. What happens if n is equal to 2? You get a quadratic. N equals 3. You get a cubic, so on and so forth, right? But which one are we going to pick? Can we start with the general case like this? Yes, some polynomial problems, you have to use the general case. And you have to assume that, okay, suppose the degree of n, the degree of p of x is n, and then plug it in and you'll get a complicated equation. But in this case, you don't really need to do that. You can do it. That's gonna, give you some trouble, but at the end, it should work. Now, take a look at this carefully. For example, first think, can p of x be a constant? Well, if p of x is a constant, like let's say, and I want to erase this area quick. So suppose p of x is a constant c, right? Then p of x plus 1 is also going to be a constant. Why? Because p returns always a constant, the output, right? All the inputs are just going to match up with a single number, which is a constant. That's what a constant polynomial is. But then if you add these up, c plus c is 2c. 2c or not 2c, that's the problem. But it's not going to equal a variable expression. So you do need a variable in p of x so that when you add p of x plus 1, it should return a variable expression. So what does that look like? Okay, well, the constant didn't work. How about the next thing to look at, which is a linear function or a linear polynomial? Can p of x be something like ax plus b? Of course, I could also write it as a1x plus a sub 0 in the general case, but you can also express a linear polynomial like this, which seems a little easier, don't you think? So let's go ahead and take a look. Can p of x be a linear polynomial? And you'll realize if p of x is linear, p of x plus 1 is also going to be linear, because what you're doing is replacing x with x plus 1. That's what p of x plus 1 means, right? From a functional standpoint. And that gives you ax plus a plus b. And this is p of x plus 1. When you add them up, this and this, you're going to get another linear. Why? It's going to be 2ax plus a plus 2b. And can this equal 2x squared plus 2x plus 1? And the answer is no, because if two polynomials are equal for all values of x on the domain, which means they're identical, then the coefficient of x must equal the coefficient of x. Okay, that could happen, but we don't see an x squared on the left-hand side. That means these two polynomials can never be equal, which means p of x cannot be linear either. What's the next step? Then maybe p of x is quadratic. Can that happen? Let's test it out. P of x equals ax squared plus bx plus c. P of x plus 1 is going to be replacing x with x plus 1, which gives us this. And then we're going to go ahead and add these up. And when we do, we're going to get a lot of terms. But we want the sum to be what? 2x squared plus 2x plus 1. So that's what we got to do, expand everything and then set them equal to each other. But you probably know that from here you're going to get an ax squared and you're going to get another ax squared from the bottom one. So you're going to give you, that's going to give you 2ax squared. And now you're going to get a 2x, which is going to be multiplied by a, which is 2ax. And then there's a b here, and then there's another b here. So it's going to be like 2a plus 2b, which will be the coefficient of x. 2b or not 2b, sorry, I just had to say that. Now, the x's are taken care of. the x squared terms are taken care of. The only thing that's left are the constants. As you know, we're going to get a 1 from here, multiplied by a. That's going to be an a. And then you have a b and then a c. So it's a plus b plus c, but there's another c here. So it's going to be a plus b plus 2c, or not 2c again, right? And you want this to equal what? Let's go ahead and move this to the left so we can fit the other one here. Oh, something like this. And then we're going to bring this equal to, make it equal to 2x squared plus 2x plus 1 from here, okay? So far, so good. Now, we're going to solve for a, b, c here. That shouldn't be too hard. Take a look. If 2a is equal to 2, that means a is equal to 1. And then if this is equal to 2, again, if a is 1, this is going to be a 2. So 2 plus what equals 2? 0. So b is 0. And if a is 1 and b is 0, this sum is going to be 1 plus 2c, which is supposed to be 1, which means c is also 0. Uh-oh, what is that supposed to mean? Well, we just assumed that our polynomial p of x can be written as ax squared plus bx plus c. From here, we basically get p of x equals x squared for the only solution as our polynomial equation. Now, why did that happen? Let me show you real quick, because this is where the problem comes from, and you can always come up with questions like this and ask whoever you'd like to ask, okay? So here's what's going on here. If you look at this very carefully, you're going to realize, hopefully, that this can be written as x squared plus x squared, which is 2x squared, plus 2x plus 1. Why is that significant? Because this expression is a perfect square, and this is a perfect square, and it's just perfect. So this is x squared, this is x plus 1 squared. And of course, this is p of x, and this is p of x plus 1. And what does that tell you? Because polynomials are special functions. If this is the case, then you can safely say that, p of x is x squared and p of x plus 1 is x plus 1 squared, and that's actually true. So this works, which means p of x is x squared, and that's the only solution we have. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out aplusbi, and bye-bye.